Welcome. In this video, I'll tell you about my work on binary classification with classical instances and quantum labels. First of all, let's look at a classical scenario of binary classification. A standard example would be classification of images. So suppose we have a universe of images which consists of images of dogs and cats. And suppose we have training data of such images that are labeled. Now we feed those labeled images to a learning algorithm, and the learning algorithm should produce a hypothesis that, upon input of such an image, gives us a label, so either dog or cat, and of course the hypothesis shouldn't make many mistakes. Now one might wonder what happens if the labels are no longer classical but become quantum states. One possible application for this scenario would be learning state preparation procedures. If you prepare some states, you will typically do this by changing some parameters in an experiment. Now, what you could try to learn would be the connection between the classical parameters and the quantum state that you produce. How is this problem answered in the classical scenario? For this, I will introduce the VC dimension. This is named after Vapnik and Chervonenkis, who introduced it first, and it is a complexity measure for binary valued function classes. The VC dimension of such a function class f is defined as follows. We take the maximum over all natural numbers n, such that we can find n points in the instance space, such that for every n-bit vector b, we can find a corresponding function that, when evaluated on the ith point, produces the ith bit of the string. In other words, it's the maximum natural number n, such that we can find n points which we can label in all possible 2 to the n ways using functions from f. So now that we have this complexity measure, let's see the results that are known here. Crucially, one can characterize Puck learnability via this VC dimension. A binary valued function class f is Puck learnable. The Puck stands for probably approximately correct, so we have to succeed with high probability and have to output an approximately optimal hypothesis. Puck learnability turns out to be equivalent to finiteness of the VC dimension of the class. We can even do more, namely we can express the necessary and sufficient number of training examples in terms of the VC dimension. In detail, this looks as follows. If the VC dimension is finite, then the number of training examples necessary and sufficient for Puck learning the function class up to an accuracy epsilon and with a success probability 1 minus delta scales linearly in the VC dimension, logarithmically in 1 over delta, and linearly in 1 divided by epsilon. Here, accuracy is measured in terms of error probability. Note that this is in the so-called realizable scenario, where we assume that there actually is a function in our class that produces the perfect labels. If that is not the case, for example, if the labels are probabilistic themselves, you can get basically the same result. You have to replace 1 over epsilon by 1 over epsilon squared. And this is then called agnostic learning. Let me now describe the main contributions of this work. Namely, we try to answer a similar question for quantum labels, and we will see that again the VC dimension is the central parameter. One of the most important aspects to understand about this work is the form of the examples. Namely, these examples are pairs of xi and ρi. The xi is a classical input in some classical space x. For example, it might be a string of bits or an element of Euclidean space. The ρi is a quantum state, and we assume that it is one of two states. So before we had two possible labels 0 and 1. Now we have two possible quantum labels, either sigma 0 or sigma 1. And for our model, it is important that we do not get a classical description of this state, but we really get a copy of the quantum state. Now that we've discussed the form of the examples, let me describe the results. First of all, let me show you upper bounds on the sample complexity. So upper bounds on the number of examples that suffice for learning in this model. For all of these results, accuracy is measured in terms of expected trace distance. In the realizable scenario, we get as upper bound on a sufficient quantum training data size, something that again scales linearly with the VC dimension, logarithmically with 1 over delta, and linearly with 1 divided by epsilon. But we have an additional factor in the denominator. First of all, let me explain what the class f tilde is, of which we take the VC dimension here. This can be quite simply described by just taking a function in our class f, which then outputs upon input of x either sigma 0 or sigma 1, and creating from this a classical function by mapping sigma 0 to 0 and sigma 1 to 1. And about the second factor in the denominator, this measures in some sense the distinguishability of the states sigma 0 and sigma 1. And here E0 and E1 are the two effect operators of a two-outcome POVM. For the agnostic scenario, we actually precisely recover the result from the purely classical case. The only change is that we take the VC dimension of this slightly modified function class to cast it in a well-known form. We complement these upper bounds by lower bounds, so we give lower bounds on the size of quantum training data that is required to solve this learning problem. However, whereas our upper bounds were for arbitrary states sigma 0, sigma 1, our lower bounds are only for pure states. And here, both in the realizable case and in the agnostic case, our lower bounds have precisely the form that we also have in the classical scenario, again with the slight change of the function class to make it 0, 1 valued so that it's more natural to apply a VC dimension. So what we've shown is basically that in this modified scenario, the sample complexities are very similar to the classical case. The one exception where we see a difference is the realizable scenario where our upper bound does not yet match the lower bound because the lower bound does not have a term depending on the distinguishability of the states. Let me describe the proof strategies for these bounds. First of all, for the sample complexity upper bounds, we give a semi-classical strategy that achieves these bounds. I will now roughly sketch this strategy. Throughout this, I assume that sigma 0 and sigma 1 are known in advance. If these two states are known, then, in principle, the corresponding Holevo-Hellstrom measurement can be computed. In this strategy, we now proceed as follows. We first perform the Holevo-Hellstrom measurement on each quantum label in the training data. And then this will give rise to classical training data just by taking the measurement outcome as classical label. Note that these measurements are very simple. We measure each quantum label separately, no entanglement over the whole training data set is used. And once we've obtained this classical training data, we will treat it as noisy data in a classical learning problem, for which we can apply classical algorithms. In the agnostic case, an algorithm that achieves the sample complexity we stated before was already known. In the realizable scenario, however, we had to improve upon known algorithms for noisy learning problems and thereby derive the optimal sample complexity in this classical learning problem. For the sample complexity lower bounds, we use an information-theoretic proof strategy which was first introduced by Aruna Chalam and de Wolf. Let me sketch the proof steps. First of all, you prove that successful learning requires a large mutual information between the training data and the learner's output hypothesis. Next, you prove that if you have m quantum examples, these can give you at most m times as much information as one quantum example. And finally, you show that if you pick certain pathological distributions from which we generate the training data, a single quantum example simply doesn't contain too much information. And as in standard PAC learning, you require learning with respect to an arbitrary unknown distribution. Finding such pathological distributions is enough to give rise to low bounds. Let me finish with some open questions. First of all, if you recall the bounds that I showed you, only one of them had an explicit dependence on the distinguishability of the states. It would be desirable to better understand this dependence for the optimal sample complexity. In this work, the instances, so the parameters of the experiment, were classical and the labels were quantum. You could now simply ask what happens if, for example, the instances are quantum and the labels are classical. This would correspond to measurement procedures. Or you could try even more, namely to have both quantum instances and quantum labels. The latter would then describe evolutions of quantum systems. For our scenario, we assumed that the output hypothesis always has to produce either the label sigma 0 or the label sigma 1. What would change in this scenario if the output hypothesis could produce other quantum labels? And finally, we made the assumption that sigma 0 and sigma 1, so the quantum labels, are known in advance, and only this allowed us to apply the Holevo-Hellstrom measurement. What happens if we drop this assumption? Can we still propose a learning strategy, and will the sample complexity change? So these are some of the questions that I'm thinking about. I'd be very happy to discuss them, so if you're interested, just get in touch. Thanks a lot for watching this video.